Hi everyone, welcome back to another video for the series of differential equations. And today we will be looking at piecewise forcing functions on differential equations, whereas our solution needs to be continuous. That means that the value of the function at any point is equal to the limiting value as the function approaches from the left or the right. Well, I'm not going to play with that definition, but we do want to look for continuity. So without further ado, let's go on to our first example. Hey everyone! So this will be our first example for today's piecewise forcing functions on differential equations. So we've got here yx and plus y equals to f of x, where f of x is equal to 1 if x is less than 1 or greater equal than 0, as well as f of x is equal to 0 if x is greater or equal to 1. And we've got an initial condition here, whereas y0 is equals to 0. So we will be using two cases to solve for this piecewise forcing function, which I will call the first interval as case 1 and the second interval as case 2. And so let's solve for case 1 first. Case 1. And we know that case 1 is when f of x is equals to 1 if x is less than 1 or greater equal than 0. And so we know our differential equation is yx plus y equals to f of x. And we know our f of x here is just 1. And if we see this differential equation, you will know that this is already in the form of a linear differential equation or first order linear. But you also can solve it as a separable method. But for the sake of this video, let's just solve it for linear differential equation. Whereas we need to find the integrating factor, which is ix equals to the e to the integration of dx dx. And we know our px here is just 1, so the integration of 1 dx is just x. So our integrating factor will be e to the x here. And we're going to multiply our differential equation here with e to the x, or the integrating factor. And we will get e to the x yxn plus e to the x y equals to e to the x. And so let's check if we've done our steps properly here or correctly to find for the integrating factor. We know if we take the derivative of e to the x here, we will get this term right here, as well as if we integrate this term here, e to the x, we will get also this term here, e to the x. And so we've done everything correctly, and we can solve for this first order linear differential equation. And so the derivative of x, or d over dx, the integrating factor, times y, equals to e to the x. And to get rid of the derivative on the left hand side, let's integrate both sides. And so this will give us e to the x times y equals to the integration of e to the x dx. And the integration of e to the x dx is just e to the x plus c. So we can do this equals to e to the x plus c. And to get rid of the e to the x on the left hand side, let's multiply both sides by e to the negative x, and this gives us y equals to 1 plus c times e to the negative x. And now we know that we've got an initial condition of y0 equal to 0, and let's solve for c. Let's plug in the values for y is 0 equals to 1 plus ce to the negative 0 is just e to the 0 is just 1. So c times 1 is c, and we will get the value of c here as negative 1. And let's substitute it back to the equation that we've got here. Okay, so y equals to 1 plus, or actually it is minus e to the negative x. And we know how to graph this function, whereas the graph of y equals 1 minus e to the negative x here is just this thing here. So the domain will go from 0 until 1 here, 0 until 1. which this is the x-axis and this is the y-axis, and the graph will look somehow like this, and it is asymptotic at y equals to 1 here. And so, to make this function continuous, we will solve for case 2 using a new initial condition that we've gotten here, which our new initial condition for case 2, and I'm gonna do this example side by side so you can see clearly all of the steps that I'm gonna do here. So our case 2 here is when x is greater than 1. And using our new initial condition at this point, because it doesn't matter where it goes, but it must go from this point to somewhere to make this function or this equation continuous, okay? Because we're looking for the continuity right here. And so this point right here has an initial condition of y1 equals to 1 minus e to the negative 1, because we're just plugging 1 at the x value as the x value, and also we're plugging in just 1 actually for the x value. And so solving for our differential equation yx and plus y again for case 2 equals to f of x, and for our case 2 f of x here is just 0, so it's not 1, it's 0 now. And if I rewrite the equation or the differential equation into this form, you'll know clearly that we can use a separable method easier to solve this differential equation. And so let's multiply both sides by dx over y, and also the other side by dx over y. And I would like to leave the negative sign on the right side because I don't want to be bothered by negative natural log of y on the left hand side. So we can cross out the dx and we can cross out the y, and on the left hand side we will just get 1 over y dy equals to negative 1 dx. And integrating both sides here, okay, we will get on the left hand side natural log of y, or ln y, equals to negative x plus c. And then we can exponentiate both sides to remove our natural log on the left hand side here. So we can cross out the e, or the exponential, with the natural log, and e to the c here is just c. Remember, e to the constant is just a constant, okay? So absolute value of y equals to c e to the negative x, and removing the absolute values on the left hand side, we will get plus minus c e to the negative x. And remember, we can remove this plus or minus sign since the c, or the constant, absorb the plus or minus sign, because plus positive constant or negative constant is just a constant. So we can write our equation by removing the plus minus sign and using the new initial value condition, which is y1 equals to 1 minus e to the negative 1. We will get here, let's find the value for c. 1 minus e to the negative 1 equals to c e to the negative 1, multiplying both sides by e, so we can remove the e that is paired up with the c, or the constant, on the right hand side. We will get c equals to e minus 1. And so substituting it back here in our equation, we will get y equals to bracket e minus 1 times e to the negative x. And so we know how that is, this solution goes from x equals to 1 or more than 1. And so we can graph this solution right here. If you go back to our first graph, let's remove this. And so, graphing our second equation here, we will get something like this one. Okay? And our final solution for this first example will be y equals to this thing right here, as well as this thing right here. So, for the first interval, or the case 1, y equals to 1 minus e to the negative x. If x is less than 1 or greater equals to 0, and for our case 2 is e minus 1 e to the negative x. If x is greater or equal to 1. And so this is our solution to this first example of piecewise forcing functions on differential equation. Hey everyone, we're back with our second example for today's topic, which is piecewise function on differential equations. So we've got here y(x(n) plus 2xy equals to f of x, where f of x is equal to x if x is greater or equal to 0 and less than 1, as well as f of x where it is equal to 0 if x is greater or equal to 1. And we've got an initial condition here where y0 is equal to 5. And our steps will be the same like the previous example that we did, which we will be doing two cases again for each intervals here, which I'll label it up here. And now let's solve for our case 1 on the first interval, which is x is greater or equal to 0 but less than 1. And we know that y(x(n) plus 2xy equals to f of x, and f of x is just x, and we can solve this first order linear differential equation by first, remember, finding the integrating factor, which is equals to e to the integration of px dx, and we know our px here is just 2x, and so e to the integration of 2x dx, and the integration of 2x is just x squared, and we will get the result of our integration, e to the x squared. And now let's multiply our whole differential equation here with e to the x squared. And so this will give us e to the x squared times y(x(n) plus 2x e to the x squared times y equals to x e to the x squared. And we've done all of our steps correctly up to now by finding or calculating our integrating factor. And now we know that the derivative of x, or d over dx, our integrating factor, ex squared times y equals to x e x squared. And if we want to remove the derivative on the left hand side, we're going to integrate both sides, and this will give us ex squared times y equals to the integration of xe x squared dx. And to integrate x times e to the x squared here, we can just use substitutions, or usually, like I showed you guys in the previous examples, I like to do throwback because it is more efficient. And so doing the throwback method here, which is xe to the x squared d, and we want to take the derivative of x squared here, which the derivative of x squared is just 2x, and we can cross out the x's here, and this just leaves us with 1 over 2 e to the x squared. And so this equals to e to the x squared times y, And to get rid of the e to the x squared on the left hand side, let's multiply both sides by e to the negative x squared. Okay, and by doing it, we will get y equals to 1 over 2. Remember, and also remember, I almost forgot something here. We have a constant here, or plus c, and then we're going to multiply both sides by e to the negative x squared here. And so we will get 1 over 2 plus c e to the negative x squared. And our initial condition here is y0 equals to 5. And so let's solve for c here from our initial condition by plugging in the values for y and x's, which 5 equals 1 over 2 plus c e to the 0 is just e to the 0 is 1, so this is just plus c. So c is just 5 minus 1 over 2. So it's just like 10 over 2 minus 1 over 2 is 9 over 2. So c equals to 9 over 2 here. And substitute it back for c to our equation here, we will get y equals 1 over 2 c, which is 9 over 2 e to the negative x squared. And so this is our solution to our first graph on case 1, which our domain is from 0 to 1. And remember, we want to find a continuous function, and from the point of x equals to 1 here, we got a new initial condition that we can use later on for our case 2. And without grabbing it, finding the new initial condition, we can just simply do this. We're gonna take the limit where x approaches to 1 of 1 over 2 plus 9 over 2 e to the negative x squared. And plugging it for 1, we will get here limit x approaches to 1, 1 over 2 plus 9 over 2 multiplied by e to the negative 1 is the same or the equivalent of 1 over e. So our initial condition for our case 2 would be our initial condition right here will be y1 equals to 1 over 2 plus 9 over 2e. But if we want to make the same denominator to make this fraction simpler, we can do this. We can make everything over 2e, and dividing 2e with 2, we just get e multiplied by 1 is e plus 9. And so this is our initial condition that we're gonna use in later for our case 2 without grabbing it. Okay, so here we're gonna do case 2 on the right hand side like the previous example. I want you all to see all of the steps that I'm gonna do for solving case 1 and case 2 side by side to make it clear. So we know our differential equation is the same, y(xn) plus 2xy equals to, it's not x but it's 0 for our f of x for our case 2 right here. And so solving this, we can use also linear, which we're going to find our integrating factor again here, which our integrating factor is e to the integration of px dx. Or actually, we can use separable at this step. So we're going to subtract both sides by 2xy, okay? And so by subtracting both sides by 2xy, we will get y(xn) equals to negative 2xy, and rewriting the y(xn) become dy over dx, since we want to do separable here, equals to negative 2xy. Let's multiply both sides by dx over y, as well as the other side too, dx over y. And so crossing out the dx on the left hand side and y on the right hand side, we will get 1 over y dy equals to negative 2x dx on the right hand side. And now we want to integrate both sides, as this is the separable method. On the left hand side, we will get the natural log of y, or ln y, equals to negative x squared plus c on the right hand side. And we're going to exponentiate both sides to remove the ln on the left hand side here, e to the negative x squared times e to c. Remember, e to the c is just c, or constant. So crossing this out, we will get the absolute value of y equals to c e to the negative x squared. And removing the absolute values, there will be plus or minus sign on the right hand side, and the c will absorb it, the constant will absorb it. So this will just be ce to the negative x squared. And now, solving for c, we're going to use the initial condition here that we just found, which is y1 equals to e plus 9 over 2e. And so plugging in the values for y's and x's here, for the y we have e plus 9 over 2e equals to c e to the negative x squared is just negative 1. And so we know that we need to multiply both sides by e to get rid of the e on the right hand side in order to solve for c. We will get here c equals e plus 9 over 2. And substituting for c back in our equation here, we will get as our final answer on case 2 y equals to e plus 9 over 2 multiplied by e to the negative x squared. And so this is our solution for case 2. And our final solution will be y equals, since we have two intervals and we found two solutions for those two intervals at where they are continuous, the first one will be this. For the first interval will be this one, and the second interval will be this one. So let's make the bracket bigger since they have fractions in it. 1 over 2 plus 9 over 2 e to the negative x squared if x is greater or equal to 0 but less than 1, and also for the second interval is e plus 9 over 2 multiplied by e to the negative x squared if x is greater or equal to 1. So this is our final solution for example number 2 for piecewise forcing functions on differential equations.